Welcome back as we continue our discussion of alternating current. Today, we're going to start by a short review of the current divider, voltage divider, Kirchhoff's voltage law, and some of the battery capacity terms we learned about. Then we will dive into capacitors and inductors and start looking at things like phase shift. First, we have the voltage divider. We know this is for series circuits. And it tells us the voltage of interest is equal to the resistor of interest over the total resistance, the total series resistance that is, multiplied by the source. We have the current divider. This is for parallel circuits. And that tells us that the current of interest is equal to the total parallel resistance over the resistor of interest multiplied by the source current. We looked at Kirchhoff's voltage law, and that tells us the summation of the voltages on a closed loop is equal to 0. This is an example circuit. Let this be 12 volts. This will be an R1. This will be 2 volts, and this will be R2. For these circuits, we always do them the same way. We start in the lower left and we make a journey. We walk around the closed loop, which is exactly what this piece tells you right here. It tells you the summation of the voltages on a closed loop is equal to 0. Starting here, we say negative 12 because we're entering on the negative terminal of this battery, plus the voltage on R1, which is all behind my head. You guys should tell me that. Plus 2 volts plus the voltage on R2 is equal to 0. In our next lecture, we're going to look at this a little bit more closely. Since we know Ohm's law, E, I, R, we could say that a voltage is a current times a resistance. So we're going to replace this in the very near future with a current times a resistance. And that current will be this current right here. It will be the current that flows in that loop. Again, so we're going to substitute, instead of saying voltage on R1, we're going to say a current times a resistance, which of course is a voltage because E is equal to IR. Anyway, we'll get to that next class. Where there was Kirchhoff's voltage law, there was Kirchhoff's current law. That tells us that the summation of the currents flowing into a node is equal to the summation of currents flowing out of that node. Let's work an example. So here's a node. We'll let this be negative 10 amps. Let this be 2 amps flowing out. We'll let this one be negative 2 amps. And we'll let this be the unknown X. You'll notice that we've assumed every current is leaving in this particular case. But that's all right because we know the summation of the currents in is equal to the summation of the currents out. It just so happens that this time there's nothing flowing in. So we would record that as 0 is equal to negative 2 minus 10 plus 2 plus X. And solving for that, X is equal to 10 amperes. I believe in the last class we talked about battery capacity. Don't recall if that's in the book, and I certainly know it's not in the book at this particular point. However, it's one of those problems that we should continue to work on. Anyway, we said the capacity was the product of current and time. So you said the capacity is equal to the amp hours of the battery. As an example, suppose you're given a 200 amp hour battery and you're told that this particular battery can run the circuit for 6 hours. So a 6-hour runtime. Can you determine what the current is? I think that's pretty easy. We'll use this equation here. Capacity is equal to the amp hours. In this case, 200 amp hours. Right? So that was the capacity, right? So 200 amp hours is equal to the unknown current by 6. So in this case, we would solve for the current is equal to, let's see, the current is equal to 33 amps. Let's double check that. So 200 divided by 6, and sure enough, there you go, 33 amps. All right, that's the review. Let's move on to the primary lecture, which goes in 3 different places. We want to introduce the concept of RMS. We want to look at the attributes of a sinusoid. And we want to explore the capacitor and the inductor. So that is where we're headed. So we have 3 parts. If you were to graph direct current, we would start with 0, and then we might say that we have a voltage of 12 volts. Okay, pretty simple there, pretty boring. If you looked at this as a function of time, you would say that for all time, we have a steady 12 volts direct current. If we were to look at alternating current, we would have that same 0 reference, but now we would have a waveform that looks like this. It is a sinusoidal waveform that varies as a function of time. Now, we mentioned RMS. What RMS allows us to do is to take this simple number, like 12 volts DC, and it allows us to equate a waveform that looks like this into a single number. So when we're done, we will describe something as an RMS voltage. For example, we might talk about 120 volts AC RMS that's used in your home. And you may have seen that. If you had a meter such as this, and you were to look at it, you would see that the meter right here is a true RMS multimeter. So if we were to look at the power in your home, we would see something like this. No, we wouldn't, because we're in the wrong setting. Let's try that again. When you use your meter, you can't use the double bar, because that looks an awful lot like this, doesn't it? That looks like the double bar. You can't measure AC unless you're in the AC setting. So there you go. There's AC. Let's try this again, and we should see, there we go. 121 volts is the line voltage in my house right now. And again, that's RMS because this is a true RMS meter. While that's all well and good, we still haven't identified or described how we convert this waveform that changes in time into a single DC number. To equate the two, I propose a thought experiment. Suppose we had 2 light bulbs. So we have the filament inside and the filament inside. Now, this light bulb is connected to a DC source, and we'll let this light bulb be connected to an AC source. And we'll let this be variable. So we can change the AC voltage at will. And here's what we're going to do. You and I are going to stand in between these 2 light bulbs, and we're going to observe the relative brightness of each system. So we have DC here, and we have AC. And what we'll do is we'll adjust the bulbs so they have equal intensity. If we do that, we will have an effective value for AC. And it works out like this. We would say the volts RMS is equal to the peak voltage over root 2. So when you said your house voltage was 121 is equal to volts peak over root 2, the peak voltage of my AC waveform, 121 times the square root of 2, which gives me a peak voltage of about 171 volts. So now if we come back up here, this voltage here would be about 171, and there's also a negative peak here of negative 171. Be sure to put this equation on your note card. It's very useful to us. If we had more time, we could explore the derivation of this number, but for now, just write it on your note card and be ready to use it on your exams and quizzes. All right, so that took care of that piece. Now we're going to look at the attributes of a sinusoid. And to be sure, we've already looked at a few, where we said that there's a peak voltage. Let's go down here and give ourselves some room to work. We start with a line, and this is our time. Okay, so that's our time. And then let's draw our waveform in. We'll use a cosine this time. Okay. One cycle is from peak to peak, so one cycle. You could think of that as peak to peak, or you could think of it as 0 to 0. Either way, it's the same thing. It's one cycle, one complete revolution. We described a peak voltage, so this is V peak. And if there's a peak, by the way, this is 0, there's also a negative volts peak, which means we could talk about the RMS voltage. We could talk about a volts peak. We could even talk about a volts peak to peak, again, depending which way you wanted to go. I just measured my house voltage, and that was 121 volts RMS. We did the calculation. It's still up on the calculator here. So that's 171 volts peak. And if we multiply that by 2, we'll see that that's 342 volts peak to peak. Again, those are all ways of describing the same thing. By the way, if you see a number by itself, so if you were to see a number, 208 or 460 or 4160, if you were to ever encounter a number and it didn't have anything behind it, assume here, what do you think? Yes, assume that it's an RMS value. Because after all, if you were to measure it with your meter, that's what you would get. You would get the RMS value. If we were to take a journey, okay, suppose we start out here at 0 and we start walking. Would you agree that at any given point, this sinusoid will take on a different value? Right, so if we're here, it's going to be 0. If we're here, it's going to be 0. It's going to be some max here, and a max there. We could describe this waveform completely by saying the voltage as a function of time is equal to the peak voltage cosine 2 pi ft. Got to be careful. I don't want my t's looking like pluses. So that's 2 pi ft plus a phase shift. And a phase shift goes something like this. Suppose this is the waveform. If we have another waveform right behind it, we would say they are in phase. If they move relative to each other, we could say there's an advance in phase or a delay in phase. Here's an example. If we did this, we would say that this waveform is delayed because it occurs after the first waveform. Okay, so that's an example of a delay where we shifted in phase from one waveform to another. A few more terms while we're here. This thing called 2 pi f is occasionally called omega, and we refer to that as the angular frequency. Technically, this should have been plus or minus a phase shift because you can shift either way. Okay. If we go back to the power that's used in your house, you'll see that's 120 volts RMS, and it's 60 hertz. So if we plug 60 hertz into this, we would say the angular frequency, omega, is equal to 2 pi by 60. So omega is equal to, so turn this on, 2 times shift way down here, pi, times 60. So omega is 120 pi, or you could simply say omega is 377 radians per second. Writing the whole thing, you would say V of t is equal to, now that's volts peak. Oh, I erased it, didn't I? I believe it was 171 cosine of 377t. Okay, so that is the same thing as saying that you have 120 volts RMS with 60 hertz. In the previous lecture, we explored how the waveform, right? We described how this sinusoid, which is developed from a generator as a function of time, could be thought of as a vector on the real and imaginary axis. Right, so we might say this vector here, like so, rotating in that direction. We did that with a picture that looked like this, where we showed the curved face of a north and a south magnet. We showed magnetic flux lines flowing from the north to the south. And then we described a pivot where we had wires that were free to rotate. We probably talked about cutting flux lines and the fact that if you're going across the lines, you're making a maximum voltage. Whereas if you're going in this direction, right, so if you're up here, there's nothing at all because you're not cutting the flux lines. So 0 voltage at this point. So we can say, let's do that better. We would say 0 here and max here. And it's maximum because you're cutting the maximum number of flux lines. It might not be the best analogy, but you could picture it. You could say if we painted a dot right there, and if we watched that dot rotate around in the generator, we could think of this as a line or an arrow that's rotating. And we could talk about a V max, we could talk about a 0, and so on. You may even wonder why I'm doing this, but hold on, we'll get there. We'll find out that this type of math, where we think of the voltage not as something that varies in time, but as a silly little line, a vector, that rotates in a counterclockwise direction, makes the math considerably easier, and it allows us to talk about that phase shift that I mentioned earlier. Because a phase shift would simply be another line. So for example, that's a phase shift early, and this is a phase shift that is late. And it turns out that capacitors and inductors cause this property. Speaking of such, why don't we use this time to introduce the components? We have a capacitor, and we have the inductor. The capacitor is 2 metal plates separated by a dielectric. The inductor has a schematic symbol that looks like that, and it is a coil of wire wound on a form. We talked about this last chapter when we talked about solenoids and magnetics. For example, if you had wire, and we'll let the current be coming to you at the top and the current flowing away from you here at the bottom, if you were to draw the lines, the magnetic lines around each of these, you would find that all of the wires on top have a current, or excuse me, have a magnetic field like that, and all the wires on the bottom have a magnetic field like this, which means you're going to have a very strong magnetic flux in that direction. So an inductor is, in some respects, you could think of it as an electromagnet. But either way, there's a magnetic field that's established because of the current flowing in the wire. Both inductors and capacitors store energy. For example, I have a large capacitor here, and I have a small buzzer. And if I connect it up, you should hear it beep. Okay. You could think of a capacitor sort of like a small battery. That's not quite correct, because a battery stores energy in electrochemical, whereas a capacitor stores energy in electrostatic sense. And while we're talking about it, the inductor stores energy electromagnetically. So electrostatic and electromagnetic. In the near future, we are going to do a lab that looks like this. You'll have that power supply, and you might set it to 10 volts. We'll have a switch, a resistor, and a capacitor. For simplicity, I'm going to assume a 2 ohm resistor and a 10 farad capacitor. We'll assume the capacitor initially has 0 voltage on it. So if we put a voltmeter here, and we're going to call that VC for the voltage on the capacitor. Anyway, we're going to assume that that voltage is initially 0. At time 0, we will close the switch. And what you'll see is that capacitor will begin to charge. It will charge until it is full, at which case it will be equal to 10 volts. As a function of time, it looks like this. Again, this is time. This is voltage on the capacitor. You'll see that the voltage on the capacitor becomes equal to the supply voltage after a certain amount of time has passed. As a rule of thumb, it takes 5 time constants, which we'll symbolize by the letter tau. So at 5 time constants, the capacitor will be considered full. I'll explain what those are in a moment. Another thing you'll want to know is that in 1 time constant, the capacitor will have about 63.2% of its charge. So at 1 tau, at 1 time constant, the capacitor will be charged to 63.2%. Now, what's tau, you ask? Well, tau is equal to the time constant. And for us, you would say that tau, my pen's broken, but that's the best I can do. We would say that tau is equal to the product of a resistor and a capacitor. For our circuit, tau is equal to 2 times 10, which gives us a tau of 20 seconds. So for this, 1 tau would be 20 seconds, and 5 tau would be 100 seconds. By the way, 10 farad is a pretty big capacitor, so it takes a long time to charge. This line can be represented mathematically by the equation: the voltage on the capacitor as a function of time is equal to the source voltage, 1 minus e to negative t over tau. Again, where tau is equal to RC. That looks like something you need to put on your note card. Let's see if we can work an example. So solve for voltage on the capacitor at t equal 5. That shouldn't be too hard. So voltage on the capacitor at second 5 is equal to the source, which we defined as 10. So 10, 1 minus e to the negative t, in this case 5, over tau, which we said was 20. At least I think we did. Yep, so tau is 20 with a c, seconds. Turn on the calculator. 10 times, parenthesis, 1 minus shift, and it's this button right here, e to the x. Then you go negative 5 divided by 20. But be careful. If we just put the parenthesis here, you see that it's in the wrong spot. It's too small. So back up. Use this arrow here. Shift and moves it down. Now you can put the large parenthesis there. So that tells us the voltage on the capacitor at 5 seconds is 2.21 volts. If we were to look at the graph, that means we are approximately here. We barely moved, okay, and we're at 2 volts. We could make similar curves for inductors, except this time it's not a question of voltage, it's a question of current. So this is inductor current, and this is time. We will find that the inductor will charge, or excuse me, we find that the inductor will have a maximum current of the source voltage divided by the resistance. And we have the same equation. The current on inductor as a function of time is volt source divided by R, 1 minus e to the negative t over tau, where tau is equal to L over R, and L is the unit for inductance. Here's an example. If we have a 20-volt power supply, a switch, a 5 ohm resistor, a 2 Henry inductor. So we said 5 ohms and 2 Henry. The time constant, tau, is equal to 2 over 5, where 2 Henries, that's the unit there. So tau is equal to 2 divided by 5, which gives us 400 milliseconds. Now we can move that over to our equation. We would say the current on the inductor as a function of time is equal to the source. We said 20 volts there. So that's 20 divided by R. So that's 20 divided by 5. 1 minus e to the negative t over 0.4. Rearranging that, we would say the current on the inductor is equal to 4, 1 minus e. So flip this, we'll move it upstairs. So we would say negative 2.5 t. And all we did there was we took this number and we said 1 divided by 0.4 gives us that 2.5. Okay, so we just moved it from downstairs to upstairs. As an example, we could solve for t equals 300 milliseconds. So current on the inductor at 0.3 is equal to 4. 1 minus e to negative 2.5 times 0.3. All right, 4 times paren 1 minus e, negative 2.5 times 0.3. Remember, we don't want to close the paren there. We want to shift and then close it. And that gives us the current on the inductor at that time of 2.1 amperes. As a rule of thumb, you are fully charged at time equal 5 tau. And I believe we mentioned that we achieve 63.2% in 1 time constant. So in 1 tau, you will achieve 63.2% of the current or voltage, depending if it's an inductor or a capacitive circuit. Okay, something I want you to notice. If we took an inductive circuit, so the current on an inductor, it looks like that as a function of time. We would say this is current. If we took a capacitor circuit, by the way, this is the inductive circuit, this is the capacitive circuit, we would say that we have a similar looking curve as a function of time, except this time it's the voltage on the capacitor. We haven't talked about it, but we may as well add it here now. If we were to look at the voltage on the inductive circuit, we would see that it does something like this. Okay, so this is the voltage. You almost want to say that the voltage comes first here, doesn't it? So the voltage spikes up very high, and then it decays, where the current starts at 0 and then it builds. On the capacitor, we end up with a similar situation, except this time, it's the current that starts high, and then the voltage follows. At time 0, when we close the switch, we get that high current, which then decreases as the voltage builds. We do have a mnemonic to remember that, and it goes like this. We talk about Eli, the Iceman, which means that In an inductive circuit, voltage leads current. In an inductive circuit, that's what L stands for. L is for inductor. In an inductive circuit, voltage leads current. Right? We see this voltage spike, and then we see the current come up. The ice part says in a capacitive circuit, current leads voltage. Again, in a capacitive circuit, which we define as C for capacitance, we say the current leads the voltage. Okay, hold on to your socks. This is where it gets interesting. What if we had an alternating current source and we had a resistor and an inductor? Would you agree that the current will always be behind? So Eli, the Iceman, which one of these applies? Well, it's that one right there, because in an inductive circuit, and this circuit is now inductive, that current is going to lag behind. So if this is the voltage, the current is going to be at a different angle, right? It's going to be rotated relative to the voltage. In the time domain, if this were the voltage, we would say the current lags behind. It occurs after. So let that be the current, and let this be the voltage. So there's a phase shift is what we would call that. I think earlier we mentioned that we could talk about things on the real and imaginary axis. This would be the voltage. Okay, the voltage is represented by that vector, and it occurs all on the real axis. The current would lag behind. There would be a phase angle, and we would see that the current lags behind. Because you remember, this rotates in this direction. So everything rotates in a counterclockwise direction. If you were a stationary observer at this point, looking this way, what you would see is the voltage waveform first, and then sometime later, the current waveform would go past. Again, as they all go moving in this counterclockwise direction. We're getting a bit ahead of ourselves, though. Let's go back to this circuit. You'll notice that it's missing a few things. The resistance here, R1, might have some value, for example, 400 ohms. If we have a resistor that has resistance, you would think that maybe an inductor, so this L1, might have some resistance as well. You would be right, and you would be wrong, because resistance isn't enough. Resistance doesn't account for that phase shift. It doesn't account for that delay that we mentioned. So at this point, we have to add a few new terms to our vocabulary. The first is reactance, which is a scalar. It just tells us how much. So how much resistance does a capacitor have? How much resistance does an inductor have? And then we have the word impedance. That's a little more interesting because it tells us how much and in which direction. And by now you might be thinking, oh, impedance must be a vector. How much and in which direction? For the inductor, we would say the reactance is equal to 2 pi FL. You could also say that XL, which is the reactance of the inductor, is equal to omega L, because 2 pi F is omega. For the capacitor, you would say the capacitive reactance is equal to 1 over 2 pi FC, or simply 1 over omega C. As an example, find the reactance of a 200 millihenry inductor in a 60 hertz system. To do that, we look at our note card, which should already have these two formulas on it. Then we say the reactance of the inductor is equal to 2 pi FL, and we substitute in our values. 2 pi, the frequency is 60 hertz, and the inductance is 0.2 henries. So the inductive reactance is 2 times way down here, pi times 60 times 0.2 gives us 24 pi, or we could just write 75.4 ohms. We see that reactance has units of ohms. Let's work a capacitor example. We want to find a capacitor that has 400 ohm reactance at 1 kilohertz. From our note card, we want this equation. So capacitive reactance is equal to 1 over 2 pi Fc. Now we substitute in our values. So 400 is equal to 1 over 2 pi 1000 C, because this was 1 kilohertz. We could solve that as 400 times 2 times pi times 1000. And then we invert that. Shifting to engineering units, we would say that the capacitance is equal to approximately 400 nanofarads. That's all I wanted to cover for today, but I want to take a look ahead so you can see where all this is going. You will be tempted to do something like this. Suppose you have a resistor and a capacitor in a circuit, and you know that this is a 400 ohm resistor and that the capacitor has a 400 ohm reactance. You will be tempted to use a voltage divider, and you might say something like, look, I have 10 volts here because the resistance and the reactance are equal. I can just set this to 5 volts AC, and that is the temptation. The truth is that that's not going to work. Do you see where the error is? The error is like this. This is the voltage, this is the current, and you have not accounted for the phase shift in them. If we're to do that, we need to add a little bit more information, and that's where this impedance comes in. An impedance modifies reactance, and it gives it a direction. So if we were to look at this real and imaginary plane, we would say that resistors live in the real world. Capacitors live in the imaginary plane, but they're negative creatures. The inductors live in the imaginary plane, but they're positive creatures. So if we wanted to be fussy, we would say that this capacitance is 400. Yes, that's true, but it's 400 at a phase angle of negative 90 degrees because the capacitor points straight down. So in that example, it would be 400 ohms at a phase angle of negative 90 degrees. Let's redraw that circuit. Look like this. We had 10 volts AC. That resistor, that capacitor, we said 400 ohms, and we said 400 ohms at a phase angle of negative 90. Moving back up here, we could say the resistor had 400 ohms, and again, the capacitor had 400, but at a phase angle of negative 90 degrees. What we're interested in is where do these two vectors meet? And they meet right there. We know that because it's 400 over and 400 down, that this is going to be 45 degrees. And we can also figure out what the length of this is using Pythagorean theorems. So C, because it's a hypotenuse, is root of 400 squared plus 400 squared. So C is equal to 400 squared plus 400 squared equals square root answer equals. So C is 565 ohms. I have to be careful. This is C as in A squared plus B squared is equal to C squared. This is not capacitance. That 565 is only the length of this line. From this, we would say that the total impedance is 565 ohms at a phase angle of 45 degrees. I'm going to put that in an entirely different way for you here. Would you agree that those are series circuits? Would you agree that Z, new term, Z total is 400 plus 400 at a phase angle of negative 90? I think you would. You recognize that as a series circuit where we're taking what was resistance, now we're talking about the impedance of these two elements together. Your calculator could solve this type of problem very simply, but we need to go into a certain mode first. So you go to mode, complex, and you should see complex in the screen right there. Now we enter it as 400 plus 400 at a phase angle, see the little angle there, of negative 90. And that tells us that the total is equal to 400 minus J 400. Yeah, but you kind of already knew that. It was 400 over, 400 down, gave you 565. Watch this. Our calculator can do that as well. Go shift, complex, and then 3. We're going to put it into a different mode. So there it is. The total impedance is 565 ohms at a phase angle of negative 45 degrees. Again, this had ohms as units. You may have noticed we're putting hats on top of everything right now. That indicates a vector. And a vector has both magnitude and direction. This form certainly has a magnitude and a direction. This one does as well, though, because to say 565 at an angle of negative 45 is the same as saying 400 over and 400 down. You end up at the same spot. It is a vector. We may as well finish out our problem. Again, this is a look ahead. We will nail this down in the next chapter. Our official lecture ended right there, so keep that in mind. But we're here. Let's take a look at it just to see where we're headed. The voltage out is the resistor of interest over the total resistance multiplied by the source. And I think we said that this was the voltage out for this particular problem. We would say that the output voltage as a vector is the resistor of interest, which is that capacitor right there at 400 and negative 90, over this guy right here, because that's our Z total, over 565 at a phase angle of negative 45, multiplied by the source, which is 10 at a phase angle of 0 degrees. V out is equal to, and then you come to your calculator, pren 400 at a phase angle of negative 90 divided by pren 565 at a phase angle of negative 45, close pren, equals times 10. And there it is. So it tells us the output voltage is 5 volts minus J5. So it's telling us the output voltage is 5 volts over minus J5. So the voltage looks like that. If we put that into the other form, we would say the voltage is, V out could also be expressed as 7.08 at a phase angle of negative 45 degrees. Again, these two are the same description. So the answer was not 5 volts out. It was much more interesting than that. It was actually an output voltage of 7 at an angle of negative 45 degrees. If you were to use your meter, this is what you would measure. You would have measured 7.07 volts. Hang in there, folks. I realize that this is getting a bit complicated, but these numbers, these vectors, are the key that gets us into something called three-phase systems. And three-phase systems are what our entire world runs upon. If you look at the power lines, you'll always see they come in threes. Phase A, phase B, and phase C, where this, for example, in our building, is 120 volts at a phase angle of 0 degrees. The B phase is 120 volts at a phase angle of negative 120 degrees. And phase C, 120 volts at a phase angle of negative 240 degrees. I can't stress how important this three-phase material is. Three-phase is what runs our world. It's all of our power distribution. It's all of our power generation. It's many of our motors, certainly most of our industrial motors. It's what makes the world go round. And if you hang in there, we are going to understand what all of this means in a very short amount of time. Until next time.